Assalamu alaikum, how are you everybody? In this video we'll discuss physics chapter 10 section 2 first law of thermodynamics. Objectives of our lesson. First, relate the first law of thermodynamics and the law of conservation of energy. Calculate heat, work and internal energy by applying the first law of thermodynamics, and describe the thermodynamic processes according to the first law of thermodynamics. Let's start. First of all, what's meant by the law of conservation of energy? Law of conservation of energy states that energy neither be created nor destroyed, but can change from one form to another. Let's explain or apply the law of conservation of energy on the roller coaster. As you can see that the roller car of the roller coaster here exerts work to overcome the friction force and to gain potential energy to reach point B. At point B, the cart has maximum potential energy but less kinetic energy, and it gains some internal energy. While it starts to move down, it starts to lose potential energy and gains kinetic energy. Due to the friction between the car and the track, internal energy increases. Here at point D, the potential energy is minimum and kinetic energy is maximum. Finally, we observe that the internal energy increases due to the friction force. The internal energy comes from the mechanical energy. Mechanical energy is the sum of kinetic and the potential. In the beginning, the mechanical energy is large, is maximum. Here, the mechanical energy decreases and the internal energy increases. So here the law of conservation of energy is applied, is satisfied, because the mechanical energy is changed into internal energy. This internal energy causes the cart itself temperature to increase and the surrounding air temperature to increase also. If friction force is taken into account, mechanical energy is not conserved. If the friction force is equal to 0, the mechanical energy will be conserved, it will be the same. But due to the friction force, the mechanical energy is not conserved, but the total energy is conserved. A steady decrease in the total mechanical energy occurs because the work being done against the friction force. Here, the total energy will be constant, will be conserved, the total energy. The total energy, I mean here, the mechanical, the internal energy, and so on. So the internal energy for the roller coaster, the system, and the energy dissipated to the surrounding air, the environment, are taken into account, so the total energy will be constant or conserved. First law of thermodynamics. First law of thermodynamics is an application of the law of conservation of energy. The principle of energy conservation that takes into account the system internal energy as well as work and heat. So here, exchange between work, heat, and the internal energy. Internal energy can be increased by work or heat. And the mathematical formula for the first law of thermodynamics, delta U equals Q minus W. Delta U represents the change in the internal energy. Q, the heat gained or lost by the system. And here's the work done by the system or on the system. So, The first law of thermodynamics states that the change in system's internal energy, delta U, equals energy transferred to or from the system as heat, Q, minus energy transferred to or from the system as work. The first law of thermodynamics again. The change in the internal energy, delta U, equals energy transferred to or from the system as heat minus energy transferred to or from the system as work. Here we have sometimes the work may be negative, the work may be positive, and the heat may be positive or negative. What is the sign of Q and W? If energy is added to the system as heat, the system gains heat energy, Q will be positive, larger than 0. If energy is removed from the system is cooled. So here Q less than 0 or is negative. So this is for Q. If Q equals 0, no transfer of energy as heat. If the work is positive, work done by the system, the gas expands, expansion of gas. When the gas expands, in this case, work is done by the system and the volume increases. When the volume increases, the work is done by the system and the work will be positive. If the gas is compressed, its size or its volume decreases. So work done on the system and the work will be negative. If no work is done on the system, no change in volume, the work equal to 0. Also, the increase in the internal energy would be positive and the decrease in the internal energy would be negative. Let's discuss an example. A total of 135 joule of work is done on a gaseous refrigerant as it undergoes compression. If the internal energy of the gas increases by 114 joule during the process, what's the total amount of heat of energy transferred as heat? Has energy been added to or removed from the refrigerant as heat? Okay, so here the work equals 135 and the internal energy increases by 114. What's the heat transferred to or from the system? Here, notice that work is done on the gas. Work is done on the gas. The gas is compressed. So the work is negative. The internal energy increases. So delta U is positive. As you can see in the figure, here the gas is compressed. So the work is negative. And the internal energy increases. It's heated. So delta U is positive. So the given is the work equals negative, as we mentioned, that work is negative, 135 joules. And the change in internal energy equals 114. Unknown Q. Q is unknown. So let's apply the first law of thermodynamics. Delta U equals Q minus W. Let's substitute. Delta U equals 114 and W equals negative 135. So 114 joule delta U equals Q unknown minus negative 135 joules of work. So in this case the work equals negative 21 joules. What do you observe here? The work is negative. Means what? The work is negative here. Means The sign for the value of Q is negative. This indicates that energy is transferred as heat from the system, from the refrigerant. Heat transferred out. So Q is negative. Heat is taken out. Thermodynamic processes. According to the first law of thermodynamics, as we mentioned in section 1, that we have some processes in thermodynamics. The first is isovolumetric. Isovolumetric means constant volume. The change in volume equals 0. As the change in volume equals 0, the work done, the change in volume equals 0, the work done equals 0. As the work done equals B delta V. But delta V equals 0, so the work done equals 0. So no work done. And therefore, using the first law of thermodynamics and substituting work equals 0, so delta U equals Q. So the internal energy increases if heat is added to the system, and the internal energy decreases if heat is taken out of the system. If Q is positive, delta U will be positive, and here it increase in the internal energy, and the heat is gained. If heat is lost by the system, Q will be negative, and delta U will be negative, and the internal energy decreases, and the temperature decreases. This is isovolumetric process. So the change in internal energy by the heat. The second process is isothermal. Isothermal means no change in temperature. Temperature is constant. So delta U equals 0. As the change in temperature equals 0, delta U equals 0. Delta T equals 0 and delta U equals 0. Because the measure of the internal energy is the temperature. No change in temperature, no change in internal energy. So this is isothermal. So substituting delta U equals 0 in the first law of thermodynamics, delta U equals Q minus W, and delta U equals 0, so Q equals to W. So heat is applied to the system, so the system can do work, or heat lost by the system, so work is done on the system. Okay, this is the isovolumetric and the isothermal. Adiabatic process. We mentioned that adiabatic means thermally insulated, means no heat gained or lost. Q equals 0. No energy transferred as heat between the system and the surrounding. Q equals 0. As Q equals 0, substitute in the first law of thermodynamics for Q equals 0, delta U equals negative W. So the work done can change the internal energy. The internal energy can be changed by the work done. If the work is done on the system, W will be negative. Negative times negative equals positive, and the internal energy increases. If the work is done by the system, the work will be positive. Positive times negative equals negative, and the internal energy will be negative or decreases. So this is an adiabatic process. Adiabatic, thermal isolated, means Q equals 0. Isolated system. Isolated, no energy transferred as heat or no work done on the system. Q equals 0 and the work equals 0. As Q equals 0 and the work equals 0, delta U also equals to 0, means the initial internal energy equals the final internal energy. This is an isolated system. Isolated systems, all the three variables equal 0. Q equals 0, work equals 0, and the change in internal energy equals 0. The last process, which is called cyclic process. In cyclic process, cyclic means to return back to the initial conditions. A cyclic process is a thermodynamic process in which a system returns to the same conditions under which it started. Return back to the initial conditions. Means internal energy changes and returns back again. Means the initial internal energy equals the final internal energy. No change in internal energy. The change in internal energy equals 0. The net change in internal energy, the total change in internal energy equals what? 0. Means what? Means the internal energy, it changed and returns back again to the initial conditions. It doesn't mean that the internal energy doesn't change. No, the internal energy changed, but return back again to the initial conditions. As internal energy, total internal energy equals 0, Q equals W. Heat equals work. Examples include refrigerators and heat engines. Pay attention that the difference here between the cyclic process and isothermal process. In isothermal process, no change in internal energy. Delta U equals 0. Means internal energy doesn't change. But in cyclic process, the total change in internal energy means the internal energy changed and returned back again. So this is the difference between cyclic process and isothermal process. Here in the refrigeration cycle. In the refrigerator, we have compressor or pump, tubes outside the refrigerator, and tubes inside the freezer of the refrigerator, and also we have here expansion valve. Inside the tubes, inside the pipes, we have refrigerant or a gas, coolant gas. What happens here? This is a compressor. This compressor pulls out gas from here and compresses it here. When the gas is compressed, so work is done on the gas. So its internal energy increases and its temperature also increases. So it starts to lose heat to the surrounding air. Here outside the refrigerator. So the back of the refrigerator is hot. Now the gas starts to escape from the expansion valve. Now the gas starts to expand. Its volume starts to increase. As its volume starts to increase, so work done by the gas and its internal energy decreases to becomes cold. So it becomes cold, it starts to absorb heat from the freezer and from the food inside the freezer. So here it absorbs, takes in heat from the freezer. So the freezer becomes cold. And now it's pulled again by the compressor and so on. So this is the cycle for refrigeration. And here's the signs for the heat, work, and the change in internal energy for the refrigeration process. Here at point A, heat is taken by the system, absorbed by the system from the freezer. When the compressor starts to compress the gas, work is done. Here, no work is done at point A, work equals 0. As Q is positive, delta U will be positive. At point B, when the compressor compresses the gas, work is done on the gas, so the work will be negative. and no change in heat here as the process takes place rapidly. As work equals negative, delta U will be positive, and here the change in internal energy will increase. The internal energy will increase, and the change will be positive. At point C, outside the refrigerator, here heat escapes to the surrounding, so Q is negative, and no work is done, so the internal energy will decrease. And finally, through the expansion valve, no change in heat as the process takes place rapidly, and here the work is positive because the gas does work, expands. So the internal energy is negative, decreases, and so on. This is a cyclic process. Another example is the heat engine. Heat engine is opposite for the refrigeration. Here in the refrigeration, work is done, and here the heat engine uses heat to do mechanical work. How? This is the heat engine. This heat engine takes heat from a hot tank, hot reservoir, and loses heat to a cold reservoir, the air, surrounding air. And the difference between the heat gained and the heat lost changes into work. So it's able to do work. How? By transferring energy from a high temperature substance, the boiler here at T high, to a lower temperature substance, air around the engine, at Tc or T cold. The difference between the heat gained and the heat lost is the work done. So the work done equals QH minus QC. An internal combustion engine, which is the car engine, found in most vehicles, is an example of heat engine. So internal combustion engine or the car engine is an example of a heat engine. Heat is used to do mechanical energy to move the car. And here is the cycle of the internal combustion engine. And this is the last point in our lesson. You are not asked to draw or explain this part.